Good evening, everyone. I hope you're doing well. And tonight's lecture will be on water resources. And as I mentioned in our last lecture, this is the last lecture before our third midterm, which will be a week from tonight. Again, there is no class next Tuesday, it's Veterans Day. And so after tonight, our next meeting, so to speak, will be next Thursday, and that will be for the third midterm. Because of Veterans Day, I had to cram a little extra into this lecture. So, as I mentioned in the previous lecture, this might be a little long, and I apologize for that. But obviously, you can take it in stages. You can watch it, step away from it, come back to it, read the PDF, whatever works best for you. But let's not wait any longer. Let's go ahead and dive into it and talk about water, which is one of the critical components for living things on this planet that's absolutely essential for our way of life. If you look at the planet Earth from space, it's clearly a water planet. There are huge, vast amounts of water on our planet. So, if you're an alien species who's allergic to the touch of water, this is actually a planet that you can see from space, is not one that you're going to want to visit. In terms of where our water comes from, we have what's known as the water cycle or a hydrological cycle. And this is actually what I mentioned briefly earlier, where you have evaporation or you have transpiration off the land, evapotranspiration coming off the land, evaporation from the water, and that moisture accumulates in the atmosphere, and then eventually it condenses, and once it condenses to a certain point, it falls back to the earth as precipitation. And so that is the cycle from evaporation or evapotranspiration to condensation to precipitation. And what you're looking at here is essentially variations on that, where you can see where there is surface runoff, you can see ocean currents, precipitation, snowmelt, and so on. I'm not expecting you to remember all of these different terms, but I do want you to be aware of the complexity of the hydrological cycle on the planet. But the basics, which you're going to want to know for the midterm, are evaporation or evapotranspiration, condensation, and precipitation. So make sure you remember those. Now, in terms of percentages of water on the planet, the vast amount of it is not available to us for use as living animals that require water. There is an enormous amount of water on the planet. We, as I mentioned, you look at the planet from space and you can see our oceans, and they are vast things. We also have a whole bunch of ice and snow, including glacial ice on the planet. And yes, we do have fresh water available as well. So in all of these cases, you have H2O in its various states. Remember phases we talked about at the beginning of the semester when we talked about solids, liquids, and gas. Here it's a little beyond that. In addition to those energy or matter states, you also have different salinity, different alkalinity, and so on in the water. So here are some percentages, and yes, I'm probably going to test you on these, not every single one of them, but I do want you to know that 96.5% of the water on the planet is in oceans. An enormous amount of the water is in oceans. And as you probably know, you can't drink ocean water. So, again, this is not available to us in order to sustain our lives in that sense. Other saline water would be an additional 0.9%, which means fresh water, the stuff that we do use, is only about 2.5% of all of the water on the planet. Now, within fresh water, 68.7% of that is locked up in glaciers and ice caps. And so, again, we aren't using that. It's locked up in glaciers and ice caps. We're going to talk about global climate change in the next lecture or two. And when we talk about glaciers melting, what they're doing is melting into the oceans. And so the water remains unavailable to us in many cases. There's also groundwater, which is about 30.1%. So, in terms of the water that you're used to thinking about, that we're used to using, it's only about 1.2% of the 2.5% planet wide. So, it's a tiny, tiny fraction of all of the water that is available to us. And within that surface or other fresh water, some of it is locked up in ground ice and permafrost, and then some of it is in lakes and rivers, streams, the atmosphere, and so on. So when you think about the water that we're using, and that's what we're going to talk about a lot in this lecture, again, the point to remember is that it is just a tiny, tiny, tiny percentage of all of the water that's on the planet. Remember how much is in oceans, have a good idea how much is locked up in glaciers and ice caps, and of course be aware of what kind of water we need to survive. Now, I showed you this graph earlier in our atmosphere lectures where we talk about global atmospheric circulations. We talked about high pressure zones, low pressure zones, and I believe I mentioned precipitation. And so, since we're talking about the hydrological cycle, let's talk about precipitation, where in areas where you have rising air, you have precipitation. And so, where you see that green arrow, that's right across the equator. And if you look carefully, you'll see that on the continent of Africa, there, that line is crossing the Congo River Basin, which is a rainforest. And over to the left in South America, it's covering the Amazon rainforest. So these are areas that have huge amounts of precipitation. That's where the water is being released to come back to Earth, and it's doing so because of where the moisture is in the global atmospheric circulation system. Now, as I mentioned, we've got two other areas that also have relatively high precipitation, but in this region, it usually doesn't fall as water, it falls as snow, because snow is also a form of precipitation. We talked about these areas at 30 degrees north, 30 degrees south latitude that are high pressure systems, and this is pretty much where we live, is right up here. Once again, you can see that that high pressure system, which means low precipitation, relatively low precipitation, is covering the Sahara Desert region, but it's also covering our region over here in North America. And that's why, if you remember our biome discussion, the various biomes that we have in our region are all largely characterized by the amount of precipitation they get. And in most cases, it is low precipitation. Deserts have extremely low precipitation. Chaparral and coastal shrub does not have very much, 10 to 17 inches per year on the average. Oak woodlands, 15 to 32 inches. Coniferous forests, 21 to 35 inches. That's not a lot. And in this case, again, with coniferous forests in our area and to the north of us, that precipitation falls as snow. So you have a little more being deposited, but it still is, there's a lot more runoff, there's less being absorbed, and so on. In any event, where we live and the biomes that we are used to in our region are driven in large part by the moisture available to us, which in turn is driven by the air circulation model that we talked about earlier. With all this in mind, let's think about us. Let's make this all about us. Let's think about Southern California and the number of people here who are large-bodied animals that need water to survive. And so when you think that there are almost 4 million people just in the city of Los Angeles, and if we expand that to be all of Los Angeles County, suddenly you're looking at nearly 10 million people, and all of them need to drink water. They need fresh water to survive, and yet here we are living in an area that doesn't have a lot of water naturally because of where we're located on the planet, because of precipitation associated with those air circulatory systems. If Los Angeles is too far away for you, we can jump here to San Bernardino, where there's over 200,000 people living in the area. And if you expand it to all of San Bernardino County, which includes a lot of desert, by the way, you've got over 2 million people living in San Bernardino County. And again, maybe not as populous as Los Angeles or Los Angeles County, but still, over 2 million people is an awful lot of people who need to drink water on a regular basis in order to survive. So that probably brings up the question, I hope, for you, where do we get our water? And we don't get a lot of it locally. We get it from outside Southern California. And yes, I'm going to test you on all of this. We get our fresh water from three major sources: the San Joaquin Sacramento River Delta, which comes down to us via the California Aqueduct, the Eastern Sierra Nevada, which comes down to us via the Los Angeles Aqueduct, and the Colorado River, which comes into our part of California via the Colorado River Aqueduct. All of these are sources of fresh water that come down to us here in Southern California that we depend upon in order for our cities to continue to survive and for the people to continue to survive. So let's talk about some of these different freshwater sources. The San Joaquin Sacramento River Delta is up in the Bay Area. And what you can see here, this is a map showing the Sacramento River, and it's coming down from the Mount Shasta area, from Lake Shasta past Redding, Red Bluff, Chico, and so on, all the way down to to Sacramento. Uh, and then you have the San Joaquin River, which is coming off the Western Sierras. It's snowmelt from the Western Sierras. You can see Yosemite Village there. This is flowing past that, down into the valley, and then hooking upwards where it intersects with the Sacramento River coming down from Shasta, all of which ending up in the Delta region there. Okay, so lots and lots of water there from these two river systems. That water is then pumped down to us via the California Aqueduct in something known as the State Water Project, which we're going to talk about a little more a little later in the lecture. But basically, the State Water Project, the California Aqueduct, brings us our water. I hope you appreciate that I drove up into Kern County to take this picture for you. I mean, I really am looking out for y'all. Here's a diagram from the California Department of Water showing the route of the California Aqueduct coming from up in the Bay Area and all the way down through the Great Central Valley and then down into our part of Southern California and also reaching over into Los Angeles a little bit and then over along the coast. Now, the reason I mentioned the Great Central Valley is because, as we discussed, that is a huge agricultural concern. They produce an enormous amount of the the agriculture for our nation. It's one of the main money makers for California. This is another shot from up there. These are actually pistachio groves, and this is what many people, you can go and find acre after acre after acre of pistachio groves and almond groves up in this area. This is up near Kettleman City in Kern County, right along the California Aqueduct. And the reason I bring this up is that pistachios and almonds are relatively drought tolerant plants. And so they don't need as much water as some other plants, like, for example, cotton. So if we look through time from the 1990s on, you can see how the different kinds of plants that were being grown in the San Joaquin Valley and the Great Central Valley has changed through the years. And what you can see is things like cotton has really kind of been depressed. Things like alfalfa is very water needy, and so it is depressed. And yet almonds and pistachios have really taken off because they're able to do better and make a bigger profit in areas that have less water available to them. And when you have drought years, which frequently happen in California, we're going to talk about that in a moment. It's helpful to have a plant that is somewhat drought resistant so that you can continue to produce the fruits of those plants, in this case almonds and pistachios, and manage to get by even when times are tight. Now, that doesn't mean the farmers in the Central Valley are terribly happy about the situation. And so if you were to drive up there, again, as I just did, so I could take this picture, what you'll see all along the road is a lot of these signs that complain about the lack of water. The thinking is that water is being dumped out of the state of California. It should be retained in the Central Valley to enable better agriculture, to enable growing more crops, and so forth. And on the one hand, you can maybe see that perspective, but there's more to it than that. There's a lot more to it than that. For one, the way agriculture is conducted in the Central Valley isn't necessarily the most efficient. In many cases, they're using relatively wasteful watering processes in order to grow their plants. And so it would be very expensive, time consuming, and probably cut into profits in order to switch over to a less water wasteful way of doing agriculture. Even with that in mind, many of the farms up in the Central Valley are making an effort to try and reduce runoff to reduce the amount of water that they're using, but still there's only so much available to them. There's also the problem that in times of drought, because you have a delta up there, a delta is where the fresh water comes down out of Shasta, out of the Western Sierras, and so forth, and heads out to the sea, just like rivers are supposed to do. But during periods of drought, you have less runoff, and so you have less water flowing to the ocean. And so the ocean is also in that delta area, and it starts making inroads and it starts coming inland. And that starts harming local ecosystems, it starts impacting local agriculture, and so forth. And so, as a consequence, one of the reasons that water is released is to try and maintain the balance between freshwater and saltwater in the Bay Area, both to preserve ecosystems and also to encourage the health of agriculture and the health of people in that area. That's what happens in time of drought. In times of plenty, this is a map of reservoirs throughout California and adjacent states. All of those circles of varying colors are reservoirs. And the point I'm trying to make with this, and I may very well test you on this, is just about anywhere in California that you can safely and reliably build a reservoir, there's one there already. They've already been built. So, in terms of building facilities to hold on to more water, there are very, very, very few places where that can be reliably and safely done. As we mentioned in a previous lecture, we are in earthquake country, and so being aware of that, it can be very fraught to make reservoirs, and so people have been doing reservoirs for good gosh, over a century. To the point where pretty much anywhere you look, you've got reservoirs and dams and so forth. And that needs to be recognized as well, that there's only so much you can do to store sources of water. And finally, perhaps the biggest reason the State Water Project is taking water out of the Great Central Valley is because of where it's going, and that's to us. This is where the population is. This is where, millions upon millions of people who need that water are living. And so dedicating it to crops is important, but dedicating it to people's lives is equally important because, again, we don't have enough water here to sustain ourselves. So, for better or for worse, this is the way California's water system is set up. And it's not just you, it's not just me, it's not just Los Angeles. Please keep in mind that the State Water Project heads all the way down to San Diego, down there at the bottom of the state. And that is a major city as well. And so they need to have sufficient funds. In fact, for the past several decades, San Diego always complains about being at the very end of the system because they are always concerned that they aren't going to get enough water. And that is an absolutely justifiable concern based on the way water works here in California. So that's the state water system. That's one system. The next one, the Los Angeles Aqueduct, gets its water off of the eastern Sierra Nevada. Remember the river system we just talked about, the Delta system. The San Joaquin River is getting its water off of the western Sierra. The eastern Sierra also produces snowmelt that feeds down into the Owens River system, what used to be the Owens Lake system. And we've talked about this, I believe, briefly when we talk about things like tufa towers. We're going to talk about that in a minute. This is Mono Lake. And these are features that we're going to talk about in a moment that are a part of this system. Now, the snowmelt comes from the Sierra. This is what a satellite image shows of the snowpack over the Sierra in April of 2025, this year. So it wasn't a terribly pronounced snowpack. Compare that to the year 2023, just a couple of years ago, when we had an enormous amount of precipitation in the Sierras. And as a consequence, the whole area was just covered with snow. You had huge amounts of fresh water available. You even had, this is Yosemite Falls in the Yosemite Valley. I love this picture. I'm not going to test you on it. I found it online somewhere. But that is the falls, and they are freezing as they fall. So instead of contributing to the river, they are building up a little ice mountain there. It was so cold that the water was flowing, but then as it fell, it froze and landed as snow. How cool is that? literally. Anyway, the reason we had that precipitation was because of a phenomenon known as atmospheric rivers, which move in from tropical regions and then they are uplifted. And as they're uplifted, they cool. And if they're carrying a lot of moisture, when they move upwards and they cool, that moisture drops out. And so you can have atmospheric rivers dropping in an enormous amount of water, either as fresh water or rain or as snow in California as they're coming in from more tropical regions off of the ocean. I bring that up because that's where that amazing snowpack in 2023 came from. But we've had atmospheric rivers for a long time in California. We just don't think about them necessarily in that sense. For example, if you go back to 1862, there were a whole series of atmospheric rivers that came through and actually flooded much of California. This is from Sacramento in 1862. The Great Flood of 1862, which you can look up online, which is interpreted to have been derived from multiple atmospheric rivers coming through the area. How's our snowpack doing right now? Well, it's tough to call. This is from earlier this year, earlier in 2025. This is, you can see it going up through a little past April, and it's not doing too badly, but it's not nearly as impressive as the past few years. And then if you jump up to now, it's that little red thing right down there in the lower left hand corner, because the year's just getting started, the cycle's just getting started. But you can see that even this early on, we haven't had a lot of precipitation. It hasn't manifested itself as a lot of snowpack. So we'll see what happens as the winter progresses. We'll see how much we get. But keep in mind, the more snow you get, the more reliable the water that you'll be receiving later in the year from the Los Angeles Aqueduct. We also get water from the Colorado River. This comes in from over in uh, the Colorado River comes in through Arizona, through the Grand Canyon, and so forth. And so this comes in from Wyoming, Colorado, Utah, and so forth, and then heads down along the California-Arizona border, and then the aqueduct carries it over to us here in inland Southern California. Now, getting back to November of 2023, that's the year where we had that huge snowpack. I showed you what it looked like in spring of that year. And it was the first time in several years that California had been relatively drought free. You can see that there were a few areas that were abnormally dry, but for the most part, in November, just a couple years ago, we were drought free. And this compares it to the previous year. The darker the color, the more severe the drought. And so you can see that just in 1 year, from November 2022 to November 2023, because of those atmospheric rivers and because of that massive snowfall in the Sierras, we met pretty much all of our water needs. Now, what are we doing today? As of this month, as of November 4th, see, I'm keeping up to date for y'all. As of November 4th, you can see that we're getting into moderate drought in much of San Bernardino County and actually severe drought in southwestern San Bernardino County and also western Riverside County and down in San Diego County. So we are returning to drought conditions. Remember the snowpack graph I just showed you, which shows it's really not doing very much so far. We'll see what happens, but at the moment in our area, we're very much back in drought conditions, so we need to be careful how we're using our water. Now, I will almost certainly test you on this. It's cool, but it's also an important point because one of the key factors of all of the aqueducts I just mentioned, the California Aqueduct, the LA Aqueduct, and the Colorado River Aqueduct, is that to get to us, they all have to cross the San Andreas Fault, which means in the event of a major earthquake, a major movement along the fault, all of those aqueducts are going to be broken. By definition, they are built out of concrete. They are not in a position to withstand major earthquakes. So if the Pacific plate jigs one way and the North American plate jags the other way, and they just shear past each other, they're going to shear all three of those aqueducts, which means we won't have any sources of fresh water coming in from those aqueducts probably for weeks, if not months. It will take a long time to reconstruct them and get the water flowing again, and that assumes no aftershocks. And that's why down in Hemet in Riverside County, the Metropolitan Water District of Southern California developed what is known as Diamond Valley Lake. It is Southern California's largest freshwater reservoir. It was excavated in the 1990s, during which period I was working at the San Bernardino County Museum, and our team there was excavating any number of Ice Age fossils of mastodons, mammoths, horses, bison, ground sloths, and saber-toothed cats, and dire wolves, and short-faced bears, all of the stuff, to the point where we found some absolutely beautiful material. That is a mastodon skull that we found as part of this reservoir project. Yes, I am bragging, and you're just going to have to deal with it. That's a mastodon skull sitting next to Kathleen Springer. She was the lead paleontologist, the lead scientist for that effort. So we were all working for her, and she directed that work from 1993 to 2003. So this water project produced these fossils. The point I'm bringing up, though, is that because this is in Hemet, it is sitting over here with us on the Pacific plate. It is not on the North American plate. All right? That's important because in the event of a major earthquake, you have 800,000 acre feet of water when the reservoir is full available to tide us over until the various aqueducts have been repaired and are flowing again. You've got several weeks worth of water available here. This was built planning for the eventuality, the certain eventuality that at some point there is going to be a major quake that we need to deal with. The fossils were a happy byproduct. We do have our own local sources of water because we do have local snowfall and snow melt that flows down into the valleys. And so here in our area in San Bernardino County, we have the Bunker Hill groundwater basin. And probably if you've driven along some of our freeways, you have seen some of these depressed pits that during the winter and spring will hold water and then they will dry out during the rest of the year. But they are retention areas for holding on to water so that when you have rainfall, when you have snowfall and snow melt, you're able to trap some of the water and make it available for our use. So this shows you, you can see there Redlands and San Bernardino labeled, and you can see that we're all within the Bunker Hill Basin. But you've also got a number of other basins there that are like the Yucaipa Basin, the Beaumont Basin, San Mateo Basin, and so on. Each of these are water catchment basins in order to preserve our local water, in addition to bringing in water from various other entities like the State Water Project or the LA Aqueduct or the Colorado River Aqueduct. So that's where we get our water. How do we use our water? Well, in the United States, as you can see from this graph, agriculture is a big number one. All right, so yes, I will probably test you on that. About 42% of water use in the United States is agriculturally driven. Now, there's a couple of different ways that we use water. Number one is you withdraw water, you pull it out, and that's water that's diverted or withdrawn from a source of surface water or groundwater. Water consumption is something else again. Water consumption is water that is permanently withdrawn from its source. It no longer goes back. It's no longer available after use because it's evaporated or it's gone into plants and then been transpired or it's been incorporated into products or crops or consumed by people or poisoned by chemicals or what have you. It's been removed from the immediate water environment. And so in the United States, agriculture is responsible for 42% of water withdrawal, but 80% of water consumption, largely because of the plants that are transpiring it. All right. Keep those numbers in mind as well, because I will almost certainly be testing you on that. 42% of water withdrawal, but 80% of water consumption. That's the United States. In California, it's even a bigger percentage. This is the water that's used for irrigation, irrigating crops and so on is 60%. And then if you continue, if you assume that things or you consider things like livestock to be part of agriculture, which I would, that's another 0.5%. Aquaculture is another kind of agriculture, that's another 2.6%. And so you're getting up in a huge amount of water here in California, more so than nationally, is going to agriculture. And keep in mind that that is even recognizing the number of people who live in the big cities, in Los Angeles, Riverside, San Bernardino, San Diego, San Francisco, Long Beach. All of these areas have enormous populations. That's the public supply that you see there, 16.6%. Yes, we consume a lot of it, but we don't come close to agriculture in California. So when we have droughts, you will almost certainly, and now maybe I'm lapsing into getting political, and I'm sorry if I'm doing that. I try very hard not to do that. But just next time we're in the middle of a drought and people say you need to control your water consumption, you need to drink less, you need to flush less, blah, 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 keep in mind that that is only going to impact a small portion of all the water being consumed in the state. And the main thing you would need to do to regulate droughts or avoid the severe impacts of a drought would be to control water loss in agriculture. That's been happening. This is from way back in 2022, right before that huge series of atmospheric rivers that dumped all that snowfall in the Sierras and changed the whole picture. But this is talking about drought and how it's impacting not only environments but jobs as well. Because if you need the water in order to harvest goods and service, or harvest food, harvest agriculture, if you don't have those goods, then you don't need the people. And so it's not just impacting plants, it's not just impacting crops, it's impacting jobs as well. It also impacts some native fish. And this is back up in the Bay Area. This is a California endangered and federally threatened species known as the Delta smelt. As you can tell from the name, it lives in the Delta area, and it actually lives in that intersection between the freshwater and the saltwater that we mentioned earlier in the Delta area. And they're good indicators of environmental conditions. And so if they're thriving, it means that you've got a healthy ecosystem. If they aren't thriving, which they aren't, California considers them endangered and the federal government considers them threatened. Um, because of less water, because of warming water temperatures, because of the additions and influx of pollutants, and the introduction of non-native species, these animals are being impacted. And if they're being impacted, they are kind of a canary in the coal mine for the rest of the ecosystem. And so other organisms like other smelt, salmon, steelhead, and sturgeon are all also being threatened, being impacted. But the harbinger of that is the Delta smelt. And so that's why it has become critical in discussions about California's water, because if you can preserve these organisms, if you can continue to maintain them as a viable species, that indicates that you're able to conserve the environment in which they live as well. So that's again how we get our water, how we use our water. Now, how do we as people individually use our water? Well, here's another graph from back in 2010, but it still pretty much holds up. And what I want you to notice is for us humans, the two big things we use water for are toilet flushing and watering our lawns. And so both of those are areas where you can work to reduce your water consumption. Keep in mind what I just mentioned, that uh, you if we reduce our water consumption as individuals and as families and as communities, we're still only impacting a small percentage of all the water consumption and the water withdrawal in California compared to agriculture. Nevertheless, it's helpful. So if you want to reduce work on your lawns, you want to reduce water use in your toilets, you can actually do that. In terms of your lawns, I would respectfully suggest, if you can, because this can, I'm not going to say it's expensive, but for those of you who live in apartments, you don't have this luxury. For those of you who live at home with your folks, it's going to be up to them. And for those of you who live either with your folks or by yourself in a place that has a homeowners association, you probably don't have the luxury of determining what goes on in your yard. So I do understand that you may have limitations in terms of what you're able to do. But if you have the opportunity, if you were in a position to do so, you might consider getting rid of your lawn altogether and replacing it with drought resistant plants, things like succulents and so forth. This is known as xeriscaping. As an aside, again, lapsing into politics, this is something I kind of wish Cal State San Bernardino would do on campus. You could still, as this picture suggests, have an absolutely glorious yard with brilliant color and a very vibrant, lively field, but you also don't have to water this all the time because these are drought adapted and desert adapted plants that don't need a lot of water. So you can reduce your water withdrawal and water consumption by xeriscaping your yard. Again, if you're able to do that. And then there's toilet flushing. And I will just tell you that I bring this up every year, and every year students just say no. And so I'm not going to argue with you, but you might consider that if you are using the toilet and you just flush it every other time rather than every time, you're really going to cut down your water use, your water consumption. Now, that's good if you are, as the kids say, doing number one or going number one. If you're urinating into your toilet, it's not going to burn you. It's not going to hurt anyone, and it can sit there for one round. Okay? Yes, that might sound gross depending on how you were brought up. I was brought up the same way. Nevertheless, it's no big deal. Now, if you're defecating, if you're pooping, if you're going number two, then yeah, you want to flush it. You don't want that stuff sitting around. But you might give a thought to flushing less frequently. If you don't want to do that, I'm certainly not going to come check out and see how many times you're flushing. I'm not that interested, but for those of you who might be open to the idea, you might consider giving it a try. It's a way to cut down on your water use that is very, very easy, very, very straightforward. There's no work to it at all. In fact, you're flushing less often, so there's less work involved. It's just being aware of the situation. So that's where we get our water. That's how we use our water. That's how we personally use our water. And now I want to change the subject completely, but still keep talking about water. So, for those of you who have driven out to Las Vegas at any point and you get out past Barstow, but before you get to Baker, have you ever looked south of the freeway, a little bit north of the freeway as well, out near Afton Road, and seen dirt that looks like this or dirt that looks like this? Next time you're going to Vegas, which I'm sure is going to be after the semester because you're too busy studying right now, but next time you go to Vegas, keep your eyes open and look south. You'll see this vista and you'll see these alternating kind of greenish and reddish bands of some really weird looking dirt. And what you're looking at is ancient freshwater lake dirt or sediment. This is the remnants of an ice age lake known as Pleistocene Lake Mannix, and you were driving past it every time you drive out to Vegas. This is an artist's reconstruction of what that lake would have looked like during the ice ages, up to about 21,000 years ago, more or less. And you can see over here is the Mojave River bleeding into it. The Mojave River is the source of all the water that filled Lake Mannix during the ice ages, up to about 21,000 years ago. So here's a map to show you the area. There's Victorville, there's Barstow, and there's Baker. And right here, that kind of tri-lobed shape in the middle there, that's Pleistocene Lake Mannix, and that was its extent during the ice ages. And it is fed by water coming off the transverse ranges, which look like this. I was very lucky one time. I got to look out the window of a plane flying over, and Mount Baldy was covered with snow. That is actually the transverse ranges. That's Mount Baldy, and that snow drains into the headwaters of the Mojave River up in the mountains right here behind campus. And then that flows down into the Mojave Desert, flows through Victorville, flows through Barstow, and during the ice ages was flowing so strongly that it made it out to these natural depressions in the ground and it filled them up and formed Pleistocene Lake Mannix. These beds that you see here are the remnant of that ancient lake. And if you know where to look, you can actually find fossils of Ice Age mammals that were coming to the lake and drinking and eating the food that was growing next to the lake and so on. That is actually the knee joint of a camel. If you feel motivated to do this, please be aware this is federal land. These fossils are protected. It's illegal to collect them without a permit. So please don't look at this and think, let's go do something this weekend. Number one, because you've got to study for the midterm. But number two, because if you try to collect these, there are serious penalties and even jail time associated with them. But there are fossils out there of animals like camels and horses and bison and ground sloth and mammoths and so forth. So it's a relatively rich assemblage. All of these animals able to live in that area because of the water of the lake and then because of the food, the plants that were being supplied by the water from the lake. Now, this is something you can do, and it's not illegal. Is if you're driving to Vegas and you get to Afton Road and you want to see something kind of cool, pull off the road. This is if you're heading to Vegas. This is when you're heading from California to Vegas along the 15 freeway. And get off at Afton Road, hang a hard right, and then an immediate other hard right. And there's a road right there adjacent to the off ramp. And you drive down, and you will see this outcrop of sediment. And the reason it's so cool, are you ready for this? I hope so, is that what you're looking at there is the ancient desert sediment. And I want to emphasize that this area was a desert during the ice ages because remember, deserts are driven by precipitation, by the amount of precipitation. That's one of the key defining things. You can have very hot deserts, you can have very cold deserts, but deserts are determined by the amount of precipitation. And so these sediments here, this big block of dirt, represents an ancient ice age desert from this region. And then these kind of layered sediments, these more greenish sediments, that's the lake. That's when the Mojave River started filling these basins, and as they filled and as the lake expanded, it moved into this area next to what is now Afton Road, and it started laying down lake sediments that you can still see today. How cool is that? You can see the transition from a desert to a lake bottom right there. And right there in the middle, do you see that white line? You find stuff like this. Would you like to know what that is? I hope you would, because that is more tufa, which I mentioned earlier. Tufa is a porous rock made up of calcium carbonate formed by precipitation from water. Formed by precipitation from water. Remember that. I will be testing you on tufa because this tufa that you can see off Afton Road out in the middle of the Mojave is very similar to the tufa I mentioned earlier up at Mono Lake, which is part of the Owens River system. That is where the Eastern Sierra are feeding into. And the reason I'm coming back to Mono Lake is because I just told you tufa forms underwater. So these towers formed underwater, and clearly they are above water now. So clearly the lake level has gone down since these things formed. And that's because Mono Lake is a part of the entire Owens River system, the Owens Lake system. And since that has been tapped into for the Los Angeles Aqueduct to come on down, this is why the lake levels in Mono Lake are going down, and this is why Owens Lake has largely disappeared. This is what it looks like from the air now. You can see the mountains there, and you can see that that is one very dry lake. It's people aren't building on it, but they certainly aren't boating on it or swimming on it because the water is all heading south to Los Angeles. It wasn't always like that. Owens Lake used to be a shallow lake left over from the Pleistocene that still had water in it. And then in the early part of the last century, early part of the 20th century, William Mulholland decided that that water source was a perfect resource to be taken advantage of in order to enable the city of Los Angeles to grow and become more populated because there would be enough water to support a much larger population. Prior to that, up in the Owens River Valley, you had a lot of growth. You had agriculture. You had people running cattle up there. And as we've talked about earlier, cattle take a lot of water. They drink a lot of water and their food takes a lot of water, and yet there used to be cattle up in that area. There were even towns and communities, and I'm going to single this one out, the town of Manzanar, which look at the number of people there living in this area. And as I'm going to keep emphasizing, they're able to live there because there's enough water there. There's enough water for them to live, to raise their animals, to have orchards of peaches and apples in that area, and also to raise corn in that area. And when they got tired of all the raising, they would go down to the local water hole because there was a water hole. There was that much water available in the Owens River at this point in time. But then, beginning in 1907 and ending in 1913, the Los Angeles Aqueduct was developed, and it took all of that water out of that system and shunted it down to the Los Angeles region to enable population growth there, which means all of those orchards and all of those farms and all of those communities up in the Owens Valley um, disappeared. They blew away. There simply wasn't enough water to support those people, those communities anymore. It's not something we would probably do today, but back in the early part of the 20th century, it was seen as a net gain. So think of that next time you're visiting Los Angeles. It also impacted any number of indigenous people who were still living in the area, depending on the water and the food for their own lives and lifestyles. And as the water went away, they were impacted as well. Now, for those of you who've been through the San Fernando Valley, this is what it used to look like back in 1913, and all those people are crowded around there to watch the opening of the aqueduct to bring water into the Los Angeles area. There's Mulholland and guests, and they certainly considered this to be an amazing event. Look how well they're dressed. And it made the paper. There's the Los Angeles Times, and you can see there talking about all of the water. The glorious mountain river now flows to Los Angeles's gates. Silver torrent crowns the city's mighty achievement. This is how it was being sold, even though the people up in the Owens River Valley probably were less enthusiastic about it. Now, just a little curiosity, that's what it looks like. Right there is where the water was coming through, where the aqueduct was releasing to flow down into that chute. Here's a close up of that opening. And the reason I bring that up is that if you're driving up in that area today, maybe you have seen that tower at the top with this running cascade of water flowing down. It's even lit up at night. But next time you see that, look over here to the side. That's that original gate that opened up in 1913 and first released the floodwaters from the Los Angeles Aqueduct into the Los Angeles area. It's still there today, and you can still see it, and it's still in operation. Now, I mentioned the communities drying up, and I want to emphasize that because once again, there were people living here, there were people raising crops here, raising cattle, raising apples, raising peaches, and so on. And without the water, they simply weren't able to survive. So by the 1920s, Manzanar and other communities up in that area had pretty much dried up and blown away, and people weren't living them. And this next bit I'm bringing up because I want to emphasize the remoteness of the area. It used to be a thriving agricultural center in California, and it became a desert town. Nothing there, completely removed from where things were really happening in Los Angeles or San Francisco or Sacramento or any of those areas, which is why this remote, unwatered, unloved area became the site of a concentration camp at the beginning of World War II, when Japanese Americans were imprisoned here because they were considered to be potential threats to the United States during World War II. And so from March 1942 to November 1945, you had Manzanar in this area. And as I've tried to describe, a lot of the resources that used to be there weren't there anymore. And that's one of the reasons it was selected, was that it was now perceived so remote and so distant and so out of the way. And that was because of the way California used their waters. If you were interested, you can visit Manzanar today. It's a national monument. There are memorials there. I would encourage you to visit it and try and realize what was happening back in those days. Getting back to Mono Lake, and again, those tufa towers you see in the background are the remnants of towers that formed underwater. And one of the reasons Mono Lake is significant is that it is a stopping off point for various birds. and the birds aren't consuming the water because the water levels are so low that it's relatively saline water. But what they are eating is other critters that are there. For example, if you visit Mono Lake, you will see a lot of these flies, and flies are gross. I'm with you. I'm supposed to study biology, but flies are gross. Nevertheless, these flies are actually kind of cool because they're not like the flies we get down here. They pretty much hang out by the water and on the ground. And so if you walk past them, they will fly up a little bit around your feet and then they will settle back down behind you. They won't necessarily get up by your face. They won't fly through the air around you. They're pretty much doing what they want to do. You also have tufa towers still forming under the surface. That is a tufa tower that is forming in the water, and here is what they look like underwater. But again, emphasizing, and again, I might test you on this, these towers form underwater. So when you see them above water, that means the water used to be there and it went away. And that's what happened with Mono Lake. And so these towers are still there. You can visit them. But they're not the only ones. You can actually see other tufa towers. This is out by the community of Trona, where you had ancient Ice Age lakes that are now gone. This is over in China Lake. The name is a giveaway. China Lake Naval Base. And this is a tufa tower inside the naval base. And once again, this indicates that everything you're seeing here used to be underwater, used to be part of an inland freshwater lake that is simply no longer there anymore. And finally, these are actually river-based tufa streams or flows out near Las Vegas, Nevada, in the north part of Las Vegas, which means you had water flowing through the area and tufa forming within these rivers, and the tufa that formed has been left behind. So once again, the story of the Mojave Desert is one of precipitation, but the story of the mountains around the desert is one of snowfall and snow melt and forming rivers and lakes. Which brings us back to Ice Age Lake Mannix and some of this tufa that is still out there that, again, you can see if you want to go. I would not encourage you to pick up the tufa because if you do that, number one, it's probably going to fall apart. Number two, the more that people pick up tufa, the less tufa is there for everybody else to enjoy. So go ahead and take a look at it if you would, but also look around you. And again, I want to emphasize that is what would be called a desert pavement. If you're walking around in there and it's like 90 or 100 degrees out, you're going to say, oh my gosh, I'm in the desert. And you won't be wrong. But what I also want you to look at is look at some of these rocks and look at that stuff around the rocks. That's tufa. That is a rock that used to be at the bottom of the lake, and you had tufa growing on top of that rock. And then the lake went away, and the rock was exposed. And as it heats up during the day and cools down at night, and heats up and cools down and heats up and cools down, eventually the tufa grew brittle and it shattered and it blew away. So the rock is now exposed again for the first time since the ice ages, but you still have the remnants of tufa around it. Here's another example. There, once again, is the desert with some of those Lake Mannix sediments, and there are rocks in the foreground. And if you look at that one just below and a little bit to the right of the center of the screen, look at it up close, you can see my pocket knife on it. And in this case, the tufa hasn't cleared the top of the rock, but it is clearly starting to come off. So again, tufa forms underwater. This rock and the one next to it was under the lake. It was in the bottom of the lake, and it was there long enough for tufa to slowly grow and form around it. And now that it's exposed in the dry desert, it's starting to come apart. So it's evidence of that ancient lake. How cool is that? You can go drive and see this stuff. Next time you're heading to Vegas, if you're tired of driving, you need a little break, get off at Afton Road and look around at all the tufa. That right there is the rock coming through. So you're probably asking, well, why isn't the lake there anymore? And it's because around 21,000 years ago, it was so full of water that it breached its eastern end and flowed down into what during the ice ages we think of as Lake Mojave, but now is the Soda Lake and Silver Lake area. And it flowed through what is known as Afton Canyon. This is Afton Canyon here. Here's another view of it, and you've got the railroad going through that because it's a canyon. If we zoom in a little bit, what you're looking at here, all that green stuff in the middle of the desert is the Mojave River. I'm going to say this yet again. I really want you to take this home. This is a desert. Deserts are determined by the amount of precipitation. So all that green you see is not because of rainfall, it is because of snowfall in the transverse ranges right here where we are, that is then flowing into the Mojave River past Victorville, past Barstow, and out into Afton Canyon. What you can also notice if you visit Afton Canyon, you look across the valley, you look at those mountains in the background, and you see that kind of greenish stuff at the top there. You want to know what that is? That's Lake Manic sediments at the top, at the top of that outcrop, because that's what used to be the bottom of the lake. That's what's left of the lake. Those are Lake Manic sediments. If you get close to them, you can see that again, that it's rock underneath it, and at the very top is what used to be the very bottom of Lake Mannix, which means you were deep, deep under where Lake Mannix used to be at this point if you were visiting the Mojave Desert. So what happened is the lake crested in the eastern part, started flowing down into what was Lake Mojave, is now the Soda and Silver Lake basins. And once it drained, it kept cutting. The water was so powerfully moving that it started cutting into the rock that once had been underneath the lake. And so all of this cutting and all of that cutting is solid rock that used to be underneath Lake Mannix. And the lake was draining so fiercely, so catastrophically, that it just carved through these rocks like they were nothing, and just kept on carving until we have the situation you see today. The Mojave River still flows through there. It still is flowing into those areas, and that's why this valley was opened up. So that's why you have things like railroads that take advantage of that carved rock to make it through this area and down into the Soda and Silver Lake basins, which you can see there. How cool is that? This whole story of ice age water draining away, catastrophes, and so on, right here in your backyard that you drive past every time you go to Vegas. And that's just one story of the Pleistocene lakes and the rivers that were here in the Mojave Desert during the ice ages. What happened is after about 20,000 years ago, the last ice age ended and things started to warm up, and you started to have a lot of glacial ice melting across the continent, and you started to lose the local glaciers, and you ended up with desert pavements like this, with ancient lake beds like this that don't have much water in them at all, obviously, anymore. It's just an echo of what used to be during the ice ages. All of this is to come back to how we use water. Yes, we got sidetracked because I love talking about the past. I love talking about fossils. I love talking about ancient ecosystems. But let's bring it back to now and how we use water. Because in this same part of the Mojave Desert, out near a place called the Marble Mountains, there is a water company that has talked about water under the surface that has been under the surface since the ice ages. It is still there, and they're talking about tapping into that, pumping it out, and then shipping it into places like Orange County. So here you see Cadiz out there in the Mojave Desert near Mojave Trails National Monument. And the idea was to build a water pipeline into Orange County, which needs more water because it's down here where we are. And we talked about where we get our water. It would be nice to have another source of water available for local people, particularly in large communities like Orange County. And so that was the idea. 16 billion gallons of water per year from the California desert pumped into Orange County. And the water would, according to the Cadiz Water Project, replace itself. Right there is the key phrase, and I may test you on this, so you want to remember it. But natural recharge was interpreted to be 32,000 acre feet per year, which means as long as you had that recharge rate of 32,000 acre feet per year, you're going to continue to maintain water in the subsurface. You're going to continue to be able to pump it out. You're going to continue to be able to pump it to Orange County, and everybody's happy. Everybody's fine. Remember that number, 32,000 acre feet per year. Now, the model for this comes from what we talked about already. Owens Lake, which was drained along the Los Angeles Aqueduct to supply Los Angeles, according to Mulholland. Remember that Owens Lake is what's left of it, the Owens River system, is being supplied by snowmelt from the eastern Sierra Nevada. right? Clearly, you go up to the eastern Sierra Nevada and you can still see snow and ice up there that is still going to be melting, still feeding the river, still heading down to Los Angeles. So that system is still working. You don't have icy and snowy mountains like that out in the middle of the Mojave Desert. This is what it looks like. And you see that there's not a lot of snow up there. You do get some rainfall up there in the Providence Mountains and the Marble Mountains and so on, but it's not nearly to the same extent as what you would see in the Owens River Valley. So the question is that estimate of recharge, 32,000 acre feet per year, is that accurate? Is that reliable? And so, with that in mind, the government conducted studies, and the Department of the Interior, the United States Geological Survey, conducted a study, and they determined that you only got between 2,000 to 10,000 acre feet per year, so less than a third of what the Cadiz Water Company proposed. And keep in mind, if you're not hitting that 32,000, you don't have enough water to pump it out and send it to Orange County. The system doesn't work if you don't have the 32,000 per year. Subsequently, the National Park Service conducted their own study because there are national parks and monuments all around the Cadiz area, and they were concerned that removing the water from the system would impact local biological communities, the animals and plants that are native to the area. And they determined even smaller, between 4,650 acre feet and 7,750 acre feet per year. And that's at the best. Sometimes it was even lower than that. So, again, two separate independent studies by independent scientists, and you're nowhere near 32,000 acre feet, which is why the Cadiz project, I mean, this has been something that's been in play since I first moved out to this area back in 1991. Cadiz has been going this entire time, and the idea still hasn't kicked in because the numbers don't work. Nevertheless, the Trump administration, the first Trump administration, expressed an interest in this. And you can see this is an article from back in 2017. Then, with the income, the incoming Biden administration, excuse me, in 2022, the permit to pump the water is vacated because the feds reevaluated the situation and realized the same thing I just told you, that there simply isn't enough water to supply this. And then, even more recently, this is November 2023, the Cadiz company signed an agreement with San Bernardino County and various water agencies to reserve water supplies specifically for desert communities. So now it's not being pumped to Orange County anymore. Now it's being reserved for desert communities. Still more recently, November of last year, local tribes got involved and committed a $50 million investment. They promised $50 million to help develop water infrastructure specifically for Native American people in the region. And that's not the end of the story. Here's what they said: the Mojave Groundwater Bank include more than 300 miles of pipelines to provide new clean water supply to underserved, disadvantaged, and tribal communities in the Mojave River Basin, the Colorado River Basin, and California's Inland Empire that presently lack access to clean, reliable water. So the idea of Orange County is out. The idea of the Inland Empire and desert communities that are disadvantaged was in, and that was as of November of last year. As of June of this year, the incoming Trump administration said we can use that water not for local communities, but we can ship it to Arizona and help them with their drought. And then, even more recently, this is October of this year, because I am keeping up to date for y'all. The local indigenous groups now, instead of promising, they have actually given $51 million. They've invested $51 million to make this water available for local communities. All of this water that they are talking about, that they're discussing, that they're fighting over, has been here underground since the ice ages. Which means when we talk about ice age lakes and when we see evidence of them, just because it's ice ages doesn't mean that it doesn't have very real, very present day implications for how we are using and consuming water. And with that, that's my lecture for the evening. And that's the last lecture before our midterm, which is a week from tonight. So if you have any questions, please feel free to reach out. I'm happy to try to answer them. I will have a study guide up for you later this evening. And until next time, please take care of yourselves. Please be good people, and we'll talk to you later. Have a good evening.